In the previous lesson, we did a graph of an exponential function where b was greater than 1. So now let's do one where b is less than 1. Remember that b has to be bigger than 0, but doesn't have to be bigger than 1. So here's one where b is a fraction less than 1. It's 1/3. And let's go ahead and graph this, just because we want to see what the differences are between one that is bigger than 1 and one that's less than 1. So we could make a table by plugging in x and y values, but if we have a graphing calculator, that's by far the easiest way to do it. So let's go ahead and put y equals 1/3 x into the graphing calculator. So I'm going to go to y equals, and let's put in, oops, let's do my parentheses, 1/3, close parentheses, and then raise it to the x power. So there it is. There's my 1/3 to the x power there. And then I'm going to go ahead and look at the table first. So it goes through 0, 1, because anything raised to the power of 0 is 1. So just like in the last problem, my y-intercept is 1. And of course, raising it to the first power is 1/3. 1/3 to the power of 1 is 1/3. And 1/3 squared is 1/9. 1/3 to the third is 1/27th. And so we're noticing that as our exponents get larger, our y values are actually getting smaller. And if I go the other way with my negative exponents, my y values are getting bigger. So what this means is as I move towards the negative side on the x-axis, move to the left, I'm going to have large y values. And as I move towards the right, if I get those positive x values, my y is going to get smaller. So this is going to look the opposite of our last problem, which was y equals 3 to the power of x. Y equals 3 to the power of x started low on the left side and then increased. This one's going to do the opposite. It's going to start high on the left side and then it's going to decrease. Let's go ahead and graph this and see what it looks like. And as we suspected, it basically looks like a mirror image reflected over the y-axis of y equals 3 to the x power. So let's go ahead and sketch this out. It looks like this. It's a very swift decrease and then flattens out on the x-axis. And as we saw from the table, our y-intercept, once again, is at 0, 1. That is our y-intercept. And the domain and range are exactly the same. The domain is still all real numbers. It goes to the left and right forever. So all real numbers is the domain, or if we wrote it in the notation that we're used to, x is between negative infinity and positive infinity. But what's interesting is that the range is also the same. Even though it's a mirror image, the range is still numbers greater than 0. Y is still greater than 0. If we go back to our table, as our x's get bigger, our y's get smaller, but they're never going to get negative and they're never going to hit 0. Just like last time, the calculator will eventually show us 0 when we get to a negative 99 exponent on our scientific notation, but that's not because it actually equals 0. That's because we reached the limit of what the calculator can show us. So we are again going to have an asymptote, that invisible barrier right there. We are again going to have an asymptote at y equals 0. So our last problem, where it was y equals 3 to the x power, this was known as exponential growth. And it was called growth because it started small and then suddenly shot up over on the right side, zoomed up and increased very, very quickly. This exponential function, on the other hand, is called exponential decay. Exponential decay is when it starts very high and then flattens out. It decreases very, very quickly. Never actually decreases to 0, but decreases very, very quickly. And these two growth and decay functions we just looked at have the same y-intercept, the same domain, the same range, and the same asymptote. The only difference between them is that one of them starts small and then gets very, very high, and the other one starts high and then gets very, very small.